Okay, I'm going to talk about optimal control of athracnose using both chemical and cultivational methods. This is joint work with David Fotza at University of Ngaoundere. And here's a picture of athracnose attacking coffee berries. Athracnose is in fact a widespread agricultural problem. It is a pathogenic fungus which attacks plants. It affects numerous fruit and berry crops as well as lawns, such as golf courses. It attacks fruits, twigs, and leaves. And just one example, in just 1 year, in just one region of Italy, in just one crop, in the olive crop, it caused $71 million worth of damage. So you can imagine the worldwide damage caused by athracnose. Here's some examples of athracnose on olive, melon, watermelon, strawberry, leaves, lawn, tomato. So you may have seen lesions like this on plants. You can identify this now as athracnose. Okay, I'm going to begin with an averaged mathematical model with control. And averaged means that it's not spatially dependent. Later on, I'll show a spatially dependent model that generalizes this. And here's the model. So let's see what the different quantities are. Theta is called the inhibition rate, which expresses the reduction in maximum attainable fruit volume. If a certain inhibition rate is maintained over the life of the plant, then the maximum volume of the fruit is reduced by that amount. And here you can see that theta is, there's sort of a logistics sort of form here. The time derivative of theta is proportional to 1 minus theta, so there is saturation. Alpha is the inhibition pressure. The larger alpha is, the better conditions for the growth of athracnose. U is chemical control intensity. Notice that if U is 1, then this denominator is reduced, so this negative term is increased, which reduces the growth of athracnose. 1 minus sigma is the inhibition rate corresponding to fruit epidermis penetration. If U is equal to 1, you can see that the stable solution for theta is theta equals 1 minus sigma. And this expresses the fact that if there is chemical control, the athracnose cannot penetrate the epidermis and the damage is limited. V is cultivational control. You can see here that there are discontinuities in theta. If V, for instance, is 0, then theta reduces to 0 at time tau I plus. Cultivational control expresses the practice of removing diseased twigs, fruits, and so on to reduce the growth of athracnose. Okay. Sigma star is the detection threshold. If the inhibition rate is below sigma star, then athracnose is not detected and no control is exerted. TK are the possible cultivational intervention times. Every tau is going to be at one of the TKs, but it's not true that at every possible intervention time there is intervention that takes place. So just to remind you, intervention, discrete intervention, is expressed by V less than 1, and chemical control, full chemical control, occurs when U is equal to 1. So U equals 0 means no chemical control. Now the problem in this model is to minimize the cost functional. And this cost functional expresses the cost due to athracnose damage over the lifetime of the crop. This is the cost due to chemical control, which can be environmental and economic. This is the cost of discrete control, cost of labor. And then this is the cost of an inhibition rate, non-zero inhibition rate at harvest time, separating out the diseased berries. Okay, so that can incur an additional cost. Okay. So we have a full space-dependent model. In this case, we introduce a theta, which is dependent on x and t, and the difference in this model is this divergence term, which expresses the diffusive spread of the fungus. We also have these no flux boundary conditions, and the boundary conditions and the diffusive terms are arranged so that if you take the average of this space-dependent theta, In the case where these coefficients, the inhibition pressure and the other coefficients are space independent, in that case, this model will reduce to the averaged model. So the averaged model does, in some case, is a special case of the full space dependent model when coefficients are space independent. In this case, we also want to minimize the cost functional. In this case, we have similar costs, but now they're spatially dependent. Okay, so let's go to the theoretical results. Both the average model and the space-dependent model are well posed. Optimal control solutions do exist, both for pulse only and for pulse plus continuous control for both models. So there are existence results for all these cases. There's an expression of the functional derivatives of the objective functions with respect to the control functions. And the expression is in terms of the solution to the adjoint problem. Using this expression, we can prove a number of things. There exist optimal control solutions that are extremal, that is, at any time during the history of the disease, the controls are either 0 or 1, and that's point-wise. I'm not saying that the chemical control would be 0 throughout the history, but at any particular time t, u is either equal to 0 or 1. Similarly, v is either equal to 0 or 1. So if you do cultivational control, you'll do full control, you'll never do partial control in order to get your optimal solution. Right. Now, for the pulse-only case, that is, u is not present, but if we're just looking at v, in the case where sigma star is 0, there exists a constructive algorithm for obtaining the optimal control. And this is done using the solution to the adjoint problem. Basically, you solve backwards to find the optimum. All right, for the averaged case, that's the case of large theta, using forward methods, we have a numerical method, a good numerical method for finding optimal pulse plus continuous control. So this result is for either the averaged or non-averaged model. This result is for the averaged model only. Okay. So we have partial results in both ways. All right. So here is the expression of the objective function in the pulse-only case in the averaged model. And you can see it depends on this quantity p, which is a solution of a backwards differential equation. P in some sense can be thought of as the marginal cost of intervention, in this case, discrete intervention. Okay, so using this, we can solve a backwards equation to find the optimal solution, both for the average model and for the non-average model in the case of pulse-only control. And here's some results. This is just for the averaged model. In this case, we have an inhibition pressure that's time varying. This large peak indicates that favorable conditions for the growth of athracnose. And these results indicate the optimal solution under different cost conditions. The dotted line is with no control. And you can see the inhibition rate is going up to 1. These colored lines are for different situations of different cost scenarios. In this case, you have different final costs. Note if the final cost is 0, then less control is warranted. Now, the actual control is only exerted at these places here. And this indicates full cultivational control at these two time locations. So as the final cost decreases, as the final cost increases, more control is needed for the optimal control result. Okay. And that makes sense. This case is looking at 3 cases for costs of pulse control. In this case, the final cost is 0 in all of these cases. And you can see that the larger the cost of the intervention, of discrete intervention, the less intervention takes place. Again, for the red, the only intervention takes place at these 2 times. And as the cost goes down, more intervention is used. This is a similar plot. In this case, a constant chemical control is exerted at the same time. Here you can see the inhibition rate is limited at 0.7, and you can see that less control is necessary. In this cost scenario, there's no additional control needed in order to obtain the optimal solution. Okay, ongoing research. We're still looking for algorithms for finding optimal, near optimal strategies. One of these is to use the forward approach point-wise, and then use some relaxation methods to get interaction between spatial points in the grid. Okay, and those are our emails. Thanks for listening.